All right. So part A says, what is the direction of the induced current in A, B, C, and D? Well, this is C over here, even though you can't see it. That's what it is. All right. So if we look at this thing, as we haul this rectangle through that magnetic field, the amount of field that's in that rectangle is going to remain constant, so there will be no induced current. Because remember, it has to change. Either the area has to change or the amount of field in the rectangle has to change for there to be a current induced. So no induced current. Okay, here what's happening is it's decreasing as we haul that thing to the right. So if it decreases to the right, then, I'm sorry, let me say this again. It's going to decrease as we pull it to the right. That means that we're getting less and less field into the page, so we need to generate more and more field into the page. Let me say that again. As it's being hauled to the right, the amount of field that's inside this rectangle is going to get less and less, and the direction is into the page. So if it's decreasing, I have to point my finger in that same direction to get it to increase in that same direction. So if you use a right-hand rule, I point my thumb into the plane of the page, my fingers curl in a clockwise direction, so my induced current is going to be clockwise. It's going to look like that right there. Oops, guess I should finish this rectangle here. Okay, so it's clockwise. Alright, this one, let me see if I can see it a little better. I don't want to tell you something that's wrong. You'll be like, way to go, Miss Walker. Alright, so let's pull it up a little bit. Alright, so here we go. So for this one, it's going to be increasing as we pull it toward the top of the page. It's increasing into the page because that's what those X's are. So I'm going to use my right hand rule. I'm going to point my thumb out of the page because if it's increasing, I want it to decrease out of the page. I want to offset that change. So if I do that correctly, it's going to flow in that direction, which I'm going to call, oops, there we go, counterclockwise. And then as I go over here, no current is induced because it's going straight toward the bottom of the page, so the number of the X's that are present are not going to change. So no current is induced. So I think that was part A. Alright, so let's scroll down and see the other parts. So here we are. Yes, what is the direction of the induced current for each loop at the instant shown? Well, we already did that. Okay, now let's look at this part. Part B says, what is the magnitude of the induced current generated in loop A and B at the instant shown? Okay, so part B, I'm going to answer right here. Magnitude of the current in loop A is 0. Because we said that there was no change in the flux, so there could be no current. Alright, the induced current in B is what we need to know now. Well, let's go up and look at the data they give us. They give us the length of the wire, 0.20 meters, the width of the wire, 0.06 meters. They give the resistance of the wire, 0.02 ohms. They give us the speed, is 0.30 meters per second. And they give us 0.09 meters of their lengths are not in the magnetic field, and the strength of the field is 0.40 Tesla. So I have an equation that says that F is equal to BIL. And I also have an equation that says that the induced EMF is equal to the change in flux over the change in time. Well, the EMF is nothing more than the voltage. So if I can find the voltage and I know the resistance, I should be able to find the current. Alright, well, let's see. So that's going to be the magnetic field strength times the area over the time. And I know that area is length times width. So if I do BLW over T, length over time should be the velocity. So BL times the, Miss Walker, let's do this. BLV, that's the velocity, that's the length. I should have done width over time, my bad. Should give us the induced EMF. So we know our magnetic field has a strength of 0.40 Teslas. Our length is 0.20 meters. And our velocity is 0.30 meters per second. So that's going to be 0.06, and I'll multiply that by 0.4. So I think that's going to be 0.005 0.024, but I'm going to check before I go any further. So I'm going to pause. Alright, I'm back, and let's see if we can get this to give us what we want. Alright, so we got a problem though. If you go back and look at the diagram for B, I believe that, if I can get a pen, here we go. I believe that this is what's going on. And it's being pulled like that. So this right here is the measurement I'm interested in. So it is 0.2 meters that way, but that's not going through the magnetic field. This is what's cutting across the magnetic field. So this right here should have been 0.06 meters. And now, let me get that math right. Okay, so 0.4 times 0.06 is 0.0024 times 0.3 is 0.0072 volts. There we go. Now I need this current. Well, I is equal to V over R. V is the 0.0072. R is the 0.02 ohms. So that's the same thing as 7.2 times 10 to the minus third volts divided by 2 times 10 to the minus 2 ohms. So that would be 3.6 times 10 to the negative 1 amps, or 0.36 amps. So we finally got that figured out. Alright, so that's part B. So we're going to mouse and scroll down so we can get to part C. Alright. So it says, what is the magnitude and direction of the induced magnetic force experienced by loop C at the instant shown? Well, if I look at loop C, I think it looks like this. And it's being pulled in that direction. So it's increasing in flux in that direction. And they want to know the force. Well, let me go back and make sure I'm not telling you a lie about the picture. So I'm going to... So the picture was right, and I know that since loop B and loop C were identical, that the current through loop C is going to be that same 0.36 amps. And I know that F is equal to BIL sine theta. So B was given to us. Well, guess who doesn't remember what B is, so we'll have to go look at that. Here's our 0.36 amps. And our L is still the 0.06 meters, because that's what's dragging through the magnetic field. The sine of 90, because the current and the magnetic field are at right angles to each other. So we've got to look up the magnetic field strength, so let's go up here and see if we can find it. 0.4, okay. So we had, darn it. So there's what we had. So I have F is equal to BIL sine theta. I lost my writing. I don't know where it went, but that's okay. We can do this now. So 0.40 Tesla. Our current, again, is 0.36 amps because loop C is identical to loop B. L is 0.06 meters. And I have a sine of 90 because that's the angle between the magnetic field and the current. So I'm going to multiply this times this, and if I can do that correctly, I'm going to get 0.144, and then I do the 0.06, and I get 0.0084 newtons. And my math might be a little screwy. That might be 86. We'll check it in a minute. Now, what's the direction? Well, I'm dragging it this way. So if it's not accelerating, there must be a force in that direction. Okay? So let me check my math real quick. Yeah, I was right. It was 0.0086, so that should have been a 6 right there. But everything was good, and you could have multiplied it in your calculator and seen what was going on. All right, let's go on to D. Oh, we're on question 2 now. Okay, well, let's see if we can knock this one out. Okay, come on. All right. I'm a little frustrated. Oh, I think I know what's wrong. There we go. Had my pen on top of my tablet. Not cool. Okay. So it says a conducting rod moves to the right with a speed of 2.5 meters per second. U-shaped conductor in a uniform magnetic field, so B is 1.20 Tesla. And then it says the total resistance of the circuit is 24 ohms. The rod has a mass of 1.50 kilograms and a length of 0.80 meters. Alright, so as we drag that to the right, we're increasing the flux. More and more magnetic field is appearing in this portion of the U-shaped conductor. So there has to be an EMF induced. So EMF is equal to change in flux over change in time. So we have the length times width is the area over time. And this length is what's taking care of our business. So we're going to wind up with BLV. So if we know that that's BLV, then we have, we have our B is 1.20 Tesla. 1.20 Tesla times the length of 0.80 meters. So we're at 0.96, and then it's being pulled at 2.5 meters per second. So we have 0.96 plus 0.96 plus 0.48. I don't have a calculator, that's why I'm doing that. So that's 14 and 6 is 20. That's going to be 2.40 volts is our induced EMF. Okay? So we're going to stop for a minute. Alright, so now they want us to determine the magnitude of the current induced in the rod. Well, that's not real hard. I is equal to V over R. So I is equal to V over R. V was 2.4 volts. R was 24 ohms. So the current is 0.10 amps. That was pretty easy to deal with. Alright. Let's scroll on down and see. Oh my goodness, I'm having all kinds of times. So, oofaba. Okay. Alright, I don't know what's going on. It won't let me record the rest of this. So what I'm going to do is stop this one, title it, put it on YouTube, and then I'll do the last C and D on do a fresh recording.